One way of making amides, and in many ways one of the easiest ways to make amides, is through the amidation of acid chlorides. Acid chlorides are a highly reactive functional group, given the good leaving group. And as we know, we typically have to make them when we want to use them from carboxylic acids. Once you have them, though, they're generally very, very easy to use. And in this case, if we want to make an amide with them, all we need to do is add the appropriate amine. Now, one thing we want to keep in mind is that in this reaction, we almost always need two full equivalents of the amine that we're going to use. And as we get through the mechanism, we'll explain the reason for that. But as a result, we get a very typical nucleophilic acyl substitution reaction that forms this new carbon-nitrogen bond. So mechanistically, how does this reaction work? Well, it turns out there's not really a lot of difference between this and any of the other acyl substitution reactions. As we'll see, there's one step at the end which shows why we need the extra equivalent of the amine. But in terms of the substitution itself, the mechanism is basically the same. Lone pair on nitrogen attacks the carbonyl. We shift electrons up onto oxygen. As with pretty much every acyl substitution reaction, this is the formation of the tetrahedral intermediate. From here, the tetrahedral intermediate breaks down, and we kick out the chlorine as the leaving group. So we formed our new carbon-nitrogen bond. The only step left here is to remove this hydrogen, and that's typically done by the chloride that we just lost in the last step. That removes the extra hydrogen and gives us our final product. It is, however, this step which is the explanation for why we need two equivalents of the acid. We don't always worry about our byproducts in a lot of organic reactions. But here, the byproduct formed is hydrochloric acid. And if we have hydrochloric acid in the presence of most amines, we get an acid-base reaction. So our methylamine here will become protonated. And so for every equivalent of HCl that we form, it's going to use up an equivalent of our amine. Since there's a one-to-one relationship between the reaction taking place and the production of HCl, that means we need twice as much amine as we would normally expect. Now, a lot of neat applications of this reaction, but probably the best one is this one. And if you look this reaction up on YouTube, you can find a number of nice demonstrations of this reaction. But in this application, Notice that our carbonyl compound has acid chlorides on both ends. Our amine is a diamine with amines on both ends. So that means when they react, and these two compounds react pretty much instantaneously when you mix them together. We form, as you can see, our amide bond, but our product has an acid chloride on one end and an amine on the other end. So it can repeat this process. And basically it can continue to repeat this until it runs out of starting material. And if you do this reaction, or if you find one of the videos online where they demonstrate it, it's actually pretty neat what you see. You mix these two compounds together, and then you can just reach in, typically using like a paper clip or a piece of copper wire, and you pull out the product in these long strings. And we've made a polymer here, and specifically, this is how you make nylon. So nylon, which of course is a synthetic fiber, is just made from this reaction of acid chlorides and amines, and done in such a way that we can basically extend the chain on indefinitely.